Hello Math 263 students. In this video we'll pick up with 2.1 and hopefully get into 2.2. So we wrapped up this example. Let's take a look at a diagram. This diagram illustrates what's going on with a function in general. We have the idea of a domain, the x values. They get inputted into the function machine, and the function machine outputs an f of x, which then becomes a value of the range. Sometimes we know what this function is when they give us the definition, like f of x equals. Other times they give us those mapping diagrams and we don't know how the function is operating. We just see the input and the output. All right, guys, I'm going to change us over to slideshow view and reposition this. All right, so hopefully you can see everything in the window now. And for our next example, we are going to look at a quadratic function and take a look at this concept of f of x plus x. So when we are given f of x, we have the definition of the function. And if I were to tell you substitute x equals 5 or x equals 10, you would plug in for your x, evaluate, and be good to go. We can also do this same concept with an algebraic expression. Here they give us f of x plus h, and we can simply plug in x plus h in place of x in each place in our formula. So let's take a look at how to do that. Notice I substitute x plus h in parentheses and I have to square it. Substitute in parentheses here because we're going to need to distribute. And then also be careful when you're squaring. Order of operations says we do our exponents, then we do our multiplication. So we would work out our x plus h times x plus h. They've simplified that and cleaned that up a little bit. And then we're going to distribute. So be careful with your signs here when you're distributing. Collecting the like terms. Oops, I pressed the button there too soon. So collecting our like terms and cleaning it up as much as we can. Sometimes there's not a whole lot we can do at this point. Occasionally there'll be some terms to condense here, and you want to do that if you can. But notice that we can't condense our 4xh with our h squared term or with our h term. Okay, so those three are all unlike terms. And then we can't condense our x with our x squared. So you would just leave it like this. This is our f of x plus h. Then, if we want to find all values such that f of x equals negative 5, that's substituting our f of x or our y value equal to negative 5 on this side, and then solving. There's a couple ways to solve. Notice our slide is recommending adding 5 to both sides to make one side equal to 0. And then maybe we could solve that by factoring or completing the square or some other algebraic method. We could also put in our negative 5 over here and graph and look at Desmos and a graphical solution. We have different options. So let's look at what happens if we plug in and work out the algebra details. If you add 5 to both sides, it does factor. This doesn't happen a lot, right? It happens in book problems because a lot of times they set them up for this to happen. But sometimes you'll get something, a quadratic, where you're going to use completing the square, quadratic formula, or graphical methods, and that's okay. If you are able to factor, notice we factored into 2x minus 1 and x minus 1. We can set each factor to 0, and that gives us our two solutions. So again, go into Desmos, practice graphing this, make sure you feel comfortable getting a solution from the graph. So our next slide just gives us a new function, not the function we're looking at, and illustrates the graph. And then I think they're wanting you to look at if you had a particular y value, you would just shoot out that horizontal line. You could find intersections and solve, just like we talked about with Desmos. One of the last things in this section is the vertical line test, which we've already mentioned and talked about in relationship to our domain and range. So think about if you have a function, or if you have a graph that you don't know is a function, you can use the vertical line test. Think about sending a vertical line, and if it intersects in one place and one place only, you're good to go. If it intersects in two places, like in this picture, then for one x value, in this case they've denoted x1, there are two y values, y1 and y2. So this graph fails the vertical line test and is not a function. So we'll just reiterate that point. And we're going to move on to even and odd functions. My graph here, or my window actually cut off that even and odd. Let me fix that. There There we go. So now you can see this even and odd function title, and we want to make sure we can classify a function from its graph as either even or odd. So let's start with even. Even means that you have symmetry around the y-axis. So for an even function, think about folding your graph right here along the y-axis, like folding it like a piece of paper. If you were to fold it, these two halves would fold on top of each other. This is considered an even function. So we'll talk about the algebra of this a little bit, but that's your first way to assess. Graph it, see if it's symmetric about the y-axis. For an odd function is symmetrical about the origin, meaning if you rotate and rotate, or think about it as if you flip it over the y-axis and then flip it over the x-axis, then you have a match. So a lot of times I'll talk about, okay, flip it over the y, right, then your graph would kind of look like this, and then flip it over the x, and now it matches. Or a 180-degree rotation. So this function would be even. We would say it's symmetric about the origin. All right, guys, my slide got ahead. Let me go back to our previous slide. And for our even and odd function, our last example, we have an example that's neither. Notice if I fold through my y-axis, I don't get a match. If I flip this piece through my y-axis, so flip over and then flip through my x, I don't have a match. So this function is neither even nor odd, and that's okay. So we won't do too much more with even and odd functions right now. We mainly want to be able to analyze the graph. You may see a little bit with the algebra of even and odd functions and what that looks like with function notation a little bit, but feel comfortable graphing and evaluating from your graph. So now we'll take a look at several other types of functions scattered in here. We'll take a look at step functions or piecewise functions, and then also we'll take a look at functions defined by a scenario. So this function, on each piece or each step, it's a linear function, but then we have all of these pieces that altogether is not linear. So it fits into our section on nonlinear functions for that reason. And this one is really interesting because in our profit and cost functions, we'll often see a jump. In other words, your cost might be steady for a while, and then when you make a new item or jump to a new time, you have a jump up. So for this, the context is delivery charges, but we could think about lots of different scenarios in which this happens. Let's say you have a rental, and the rental cost you so much for the first 2 days, and then once you jump into that third day, you jump up, right? There's not an in-between. You're either paying this amount or that amount, and then that happens at different points. So a step function is very useful in helping build or model money situations. The next type we'll see is an area function in this case, or other functions that are defined by a geometric situation. So we might have something where we're building a fence or building a lot, and they describe to us how they want that fence or that lot to look. If I were to change my dimensions, it would change the area, and we can think about building an area function based on the length and the width. So sometimes they'll give us constraints like the width is supposed to be half the length, or we want the width to be a third of the length, or we want some other proportion. In this case, there was one where we were looking at a half proportion and another constraint on the total area, which allowed us to produce an area function. So again, we're not going to look at the specific context of how they're getting this right now. We'll take a look at some examples and do that on our own. But what I want you to be aware of is the idea of us taking a situation, analyzing, and creating a function that may then be nonlinear. All right, I think that wraps up our 1.1, or excuse me, our 2.1. Let's get into our 2.2. We'll focus more specifically on quadratic functions, take a look also at translations and reflections. So we're already familiar with the type of a quadratic function. We don't want our leading coefficient to be 0, because if that's the case, we would be back in the linear. So we want to make sure if we have a parabola, we know that that resulted from a quadratic function. Feel comfortable identifying some basics about the graph. We can say this parabola opens up. It has a vertex at 0, 0. Its minimum value occurs at 0, 0. The minimum for our x is 0. The minimum for our y is 0. Whereas if we contrast this with our next one, notice we just have a shift down. We'll talk more about those shifts to come. But that -4 shifted me down. I have a vertex at 0, -4. And the minimum for my y is -4. The minimum of my x is 0. We could also say the minimum is 0, -4. I see that my x-intercepts are different now. My parabola still opens up. So these are all things I want you to be able to identify. Looking at a function, being able to tell that it opens up, being able to tell that there's a shift, being able to, from the graph, read off x-intercepts and y-intercepts. So this graph is trying to illustrate what happens as you change the leading coefficient. The red is the negative x squared. Think about that as your parent function. The negative is making us open down. And the blue is negative 0.5. When we start putting that fraction in there, or that decimal, my graph almost starts to flatten out. We had negative 0.25 x squared, we would have something that's even wider. Whereas when we're looking at negative 2x squared, notice that's shrinking my function in or condensing it. What it's actually doing is for any particular x, the y is getting bigger. So that means you jump down further on the graph and it makes it steeper. Then we're even steeper still with the y equals negative 4x squared. That's my gold graph. And I could continue. Negative 10x squared would be even steeper, a parabola that opens a lot more compactly. So this graph puts some of that together, looking at different shifts. Notice our parent function is y equals x squared. They graphed x minus 3 quantity squared and x plus 4 quantity squared. This leads us into just translations. We want to make sure we understand how adding to our x is going to affect our function. So one more example. This one is a little bit less clear how we're modifying it. Notice it's not just a simple add at the end of the function or add to the x part, but you should be able to take this function, graph it, still identify the important components. Notice my vertex is not nice even numbers. My x-intercept here might be, but here is not. One thing your book will urge you to do is work on completing the square. Completing the square allows you to, without a graph, identify the vertex and some of the important features. I'm not huge on completing the square for you guys in this course. Completing the square has value and it's a good exercise, but a lot of the things that I'm going to ask you to do, you could graph it, get the same information, and not necessarily have to complete the square. So think about completing the square as something that is an optional tool for us in these situations. If you like to do it and you feel comfortable with it, it's another way to check what you're doing and what Desmos is telling you. But again, in most of our scenarios, it's not the only option. So I think we return to this one later or another one with completing the square in a little bit. But our next slide just summarizes some of these important features of a parabola. And one thing I want to point out is the vertex and the axis of symmetry. When you complete the square, you get these formulas, and we will practice using them because they're nice shortcuts, the negative b over 2a, and evaluating the function for the y value. But again, we'll use the graph as an alternative. So let's see, I think they actually gave us a different function here. So yes, this function and the one we're going to be working with are a little bit different. And our directions in this one are to complete the square, find the intercepts, the y and the x, the vertex, and sketch the graph. So let's actually pause this. My 15-minute time limit is about to cut off, and we'll pick up in our next video.